Okay, so now we're going to find out conditions. So under which basically we're going to find necessary and sufficient conditions and for a subset of a group to form a subgroup. So what's we going to do? So suppose we have a group. So if we have a group G is a group, so this is our group. So we're going to find necessary and sufficient conditions for a subset of G. So we're going to find the conditions by which we can easily say that a subset of G is a subgroup of G. So G with the same compositions induced from G will be a group for or not, we will say from the following conditions. So here we have the conditions. So this is one is a results. So results is the condition. So a subset. So first let me write, let Z be a group, then a subset. So then a subset H of G is a subgroup if and only if satisfied the following three conditions. So first condition is the identity elements of the group. So we write e.g. G for the group, E is the identity elements. We are using the notations e.g. to denote the identity element of the group is belongs to the subgroup H, and it's obvious will going to be the identity elements of the group all selves. So e.g. belongs to H. Second condition is if A and B belongs to H, then this implies their composition. So A compose B also belongs to the set H. And third condition is if A belongs to the set H, then its inverse, so A inverse also belongs to H. If these three conditions satisfied, then we will say that H is a subgroup of the group G. So if and only it means that if G is a group and H is a subgroup, so if H is a subgroup, then it satisfies these three property. And in another way to say, if and only means in another way to say, a subset for which these three conditions 1, 2, 3 holds, that subset with the induced compositions will be a subgroup of the group G. So to check, so here we have a tools to check a subset of the group is a subgroup or not if it satisfies these three properties. So these three properties in some books also has a written, they erase the first property and they only working with the last two property. Here they use that the subset is non-empty. So we just don't go to that, we just use the three property. We're going to check the elements with this composition satisfy the three property of H, the elements of H with the property satisfy this three condition or not. If it satisfies these properties, then we will say that H becomes a subgroup of G. So also these three property, so also we can write instead of last two property. So somewhere you also find that its last two property can be also written as a one property. So also you can write something like that. So first property is all be there, and from the second property and third property, instead of that two property, you can also use the only one property. It says that if A and B belongs to H, so if any two elements, so it's have to true for all AB. So if AB belongs to H, So we can write in this way that A compose B inverse belongs to H. So it's also the same thing as our previous conditions. Can you say why? So think about over it and just tell me why we can replace that last two property with this property 1. So just let's see some example where we can use this property. So we already seen something. We have seen some last day. We have so in last lecture we have seen some properties of some example of subgroups. So we're going to use the property to check a subset is a subgroup or not. So here we work with some examples. So here we have an example. So we know that Z3 with 3 elements 0 bar, 1 bar, 2 bar, and Z3 with addition is a group. So we already know that is a group. So let's next consider the subset H which contain the two elements 0 bar and 1 bar. Now we're going to check H with these same additions is a subgroup or not. So we'll check one by one. First, the H contain the identity elements of Z3 because 0 bar is the identity element. So 0 bar belongs to H. The identity element 0 bar is the identity element of Z3. So first property is okay. Next consider the second property. So we have 0 bar plus 0 bar. If I add these two we get 0 bar. So it's okay. Now if I add 0 bar plus 1 bar, so instead of doing all that thing I just use the composition table. So just erase this part and use the composition table. So what we have, so we are doing 0 bar, 1 bar. Here we have the induced additions. So 0 bar, 1 bar. So 0 bar, 0 bar, 0 bar, 0 bar plus 1 bar. So 1 bar, 1 bar plus 0 bar, 1 bar. But here we have 2 bar. Now you can clearly see that here in our previous condition A bar, 1 bar is A, and also we take B as 1 bar. So we have A, B belongs to the set H, but after the composition, so A compose B, here is 1, composition is plus. So 1 plus 1 which is 2 bar, which does not belong to the set H. So from that conditions we have talked about that. So from that conditions you can clearly say that H with the addition is not a group. So is not a subgroup of Z3. That's the beautifulness of the property. So we don't have to go through all the property of associativeness. We don't have to find the inverse of each and every elements. We just from that property we can easily say that this does not form a subgroup. So it's not a subgroup. Now we're going to check an example where it is a subgroup. So let me erase this example. So here we go. So we just erase this part. So just let's go with some examples. So here we just drop that all that thing. So we're going to have the example. We already know that the set R with addition is a group. We already know that is a group. Now the set Q of all rational numbers. So Q is a subset of R. Now we are going to check that Q plus is a group or not. So first property, we know that 1 is a rational number. So 1 is a rational number. So 1 belongs to the Q. So 1 is the identity element. No, sorry, I am sorry for that. 1 is not the identity elements over here. Here is the 0 is the identity element. So we also know that 0 is the rational. 0 is a rational number. So 0 is a rational number. So 0 belongs to Q, and here 0 is the identity element. 0 is the identity element of the group. Identity element of the group R plus. Okay, next what we know about the rational number. We know that addition of two rational numbers. So addition of two rational numbers. So addition of two rational numbers is a rational numbers. Is a rational number. So from that, so that means if I take any two elements a b from Q, which means to say a b a rational number, and we have the composition addition over here. So a plus b, because a is a rational, b is a rational, so a plus b is a rational, so a plus b again belongs to Q. So second property also true over here. So next check the third property. So if we have an elements, so if a is a rational, so it belongs to Q, means a is a rational number. So is a rational number. So because the negative of a rational number is also a rational number, so a minus a is a rational number. So because minus a is a rational number, so what we can say? We can say that clearly that minus a obviously belongs to the set Q. So here we see that all the three property satisfied by the elements of the set Q3. Sorry, all the elements of the set Q. Sorry for, I am just distracted by my phone, so I'm sorry for that. So here we go. So we have seen that all the three property satisfied over here. So it's contained the identity elements of the group, and if we take two elements after the composition of elements, that elements also belongs to the set, and if we have the elements belongs to Q, and the inverse of the elements also belongs to the set Q, so it's contained the inverse elements. So from there, from our properties from the necessary and sufficient conditions, from that we can say that Q plus is a subgroup. So here we can say that Q plus is a subgroup. So Q plus is a subgroup of the group R plus. Okay, next we are going to see another example where we can use this property. So let me erase this part first. So here we go. Just let me erase the whole parts. So in this way we'll learn the results one by one. So about group theory, so we have to go very slow and one by one. So let's go with another example. So here we have example. Sorry for the mistakes over here. So here we have the example. So we know that G is the set contain 1 minus 1, the I minus I is I square, is I is a complex number, which means I square is minus 1. So we know that G with multiplication, so G cross is a group. So G under multiplication is a group. So what we're going to do, we'll check a subset H which contain the two elements 1 minus 1, and just let's take another element. So I, is this form a subgroup or not? So first of all, first condition is content, so 1 belongs to H, and 1, we know that 1 is the identity elements of the group. So 1 is the identity element, so 1 is the identity element of Z, the group G over here. So first condition is okay. So to check second condition, we will consider the composition table. So here we take the composition tables. So what we get, so here we go, take the 1 minus 1 I, 1 minus 1 I. So 1 1 is 1, 1 into minus 1 is minus 1, 1 into I is I. So minus 1 into minus 1, 1 minus I, and I minus I, and here I into I is minus 1. But what we have seen, so we have get something dangerous thing. Here we get minus I. So here 1 minus 1 and I belongs to the set H, but if I take the composition minus 1 and I, we get minus I. So we get one pairs of elements for which this does not belong to the set H. So from that conditions, from that sufficient and necessary condition, we can say H with the multiplication, under multiplications, is not a subgroup. So this is not a subgroup. So here in this way we can check for other subset of the group, are they subgroup or not.